Antonio, and I'm one of the co-organizers of this event, ETRL, together with Bhagwan, who is sitting here, and Jack, who couldn't be here unfortunately. So thank you all for coming, and for those of you who sent papers, special thanks as well. And we're going to, I'm really happy to kick off the conference with a talk by Professor Dimitri Bersekas, who I will introduce now. I'm pretty sure he doesn't really need an introduction. I mean, people know him not only in ADP and RL, the two fields that are, let's say, represented in the core of this conference, but also way beyond, like, you know, other fields that that use this type of optimal control problem, like operations research, and also beyond that in optimization and so on. So he doesn't really need a more extensive introduction than this, I think. So I will just, without further ado, I will just give him the floor, and he's going to tell us about some new ideas regarding projected types of equations that we've seen before in LSTD and this type of solutions, but he's doing new things with them, and he's excited to tell us about that now. So, Professor Bersekas, please.
It's my pleasure to be here. I'm going to talk about dynamic programming with cost function approximation, which is certainly within the main topic for this workshop, and some new directions that I have, new research directions I've been working on together with my former student, who you may know her as Jenny Yu. And there are three directions that connect. And the first one has to do with Seminorm projections. One of the main ideas in approximate dynamic programming is to work with a projected equation. TD lambda is a method that tries to solve the projected equation, projected Bellman equation. And this projection involves a full Euclidean norm. In order to connect projected Bellman equations and aggregation equations, the two main approaches of approximate dynamic programming, full norm projections are not enough. It is necessary to use a more general form of projection based on a seminorm. Once we do that, then I'd like to show you how you can connect the projected equation approach with the aggregation approach. The second direction has to do with generalized forms of Bellman equations that involve multiple steps. Like TD lambda is a multi-step Bellman equation, and how far into the future you look depends on this parameter lambda. I'm going to talk about a generalized form of this equation that involves weights that are different for different states, and this is essential if you consider the multi-step approach together with the semi-norm projected equation that corresponds to aggregation. The third subject has to do with simulation-based implementations of the solution of this generalized Bellman equations. Those of you who are familiar with TD lambda and related methods know that you have a certain Markov chain which you simulate for an infinitely long trajectory. And then you use the samples and combine them with some complicated formulas and solve some equation that's a simulation-based approximation to Bellman's equation, the multi-step Bellman equation. Now this, again, does not work for aggregation in the aggregation context, and also has some difficulties related to exploration ideas and so on. So it is useful to consider a different form of simulation that does not involve a single long trajectory, but rather many short trajectories, and you can control the start point, which also helps with exploration. I call this free-form sampling. So what I'll do is give you an overview of these three directions, and then selectively pick on a few things to illustrate some points. Okay, first of all, what do we mean by a Bellman equation? Think of the simplest finite state MDP, dynamic programming problem, that there is, whereby you have n states and a discount factor, and Bellman's equation is the optimality equation, the dynamic programming equation, which says that the optimal cost function is a fixed point of a certain mapping, T mu. And this T mu mapping maps n-dimensional vectors J into n-dimensional vectors J, and T mu's of J. And this is the equation that corresponds to a fixed policy mu, a stationary policy mu. So here, these Pij's are the transition probabilities corresponding to the policy at state I to state J. G is the cost per stage, and this is the standard equation. So Bellman's equation is this: finding a fixed point of T mu. And there's another Bellman equation corresponding to the optimal policy, whereby the T mapping involves a minimization of overall controls rather than a fixed policy. I'm going to be focusing on a fixed policy, so even though some of the ideas apply to this type of equations, I'm going to be focusing for this talk at the top equation. Okay. Now, the problem in the main problem in approximate dynamic programming is that we're dealing with gigantic state spaces. The dimension n is very, very large, and therefore you can't store the cost vector, and you can't compute it, and there are all these difficulties. And an important idea is subspace approximation, whereby you approximate cost vectors by elements of a low-dimensional subspace. This is a subspace involving parameterized by R, a much smaller dimensional vector. Phi is a given matrix of basis functions. The columns of phi are basis functions for this subspace. And we have a cost vector corresponding to a policy, and we would like to find an approximation of that onto the subspace. Now, one idea is to project this vector down to the subspace, but that doesn't work very well. And a more common idea is Galerkin approximation, which is this projected equation, which involves finding a vector phi r that satisfies the Bellman equation, but projected. This pi here, this pi is projection with respect to some weighted Euclidean norm, with different weights for each state I. So to solve the projected equation, what you need to do is find a vector such that when you apply T mu to it and then project down, you end up at the same vector. That's the projected equation. And like I said, it's a special case of an old methodology, Galerkin approximation, which dates back to before the Second World War, and it's used extensively. It's a principal method for solving partial differential equations, for example, and other types of equations. However, what's unique about approximate dynamic programming is that it solves this equation by simulation. Okay, that's the main difference between Galerkin approximation and projected equations as you find them in approximate dynamic programming. The use of simulation is something unique to approximate dynamic programming. So, this is the TD type of equation that we try to solve. Now, there's another approach that is also old, but has not received as much attention as the TD approach. It's the aggregation approach, which in shorthand also tries to find an approximation to the cost vector within a lower dimensional subspace, satisfying an equation of this form. Phi here is also a matrix of basis functions, but there are special basis functions. Phi is assumed to have as rows probability distributions, which are sort of like interpolation probabilities. And D is also a matrix that has as rows probability distributions. And here we have this equation where in place of projection we have phi D. Okay? Now how this arises I'll explain a little later, but let's look at this equation and see that they are quite similar. Just a phi D here in place of P. Now it's not always true that phi D is a projection, but it turns out in the most important special cases it is a seminorm projection. And with this identification we can connect these two. That's the idea here. There's also a third method that we just mentioned briefly, the Bellman equation error method, or Bellman residual method, which is essentially a projected equation method, but it's a different mapping that has the same fixed points as t. So I'm not going to talk about the Bellman error method, but it's just a special case of this. So the first direction of research aims to connect all of these methods by writing them as phi r p of t mu phi r, where p is Seminorm weighted Euclidean projection. That's the first idea. Okay. Now, the second research idea is to look into generalized forms of Bellman equation. Remember that we focus on a single policy. We consider this ordinary Bellman equation. A generalized Bellman equation is one that involves a weighted form of this mapping T mu. W here is a matrix of weights, one weight per state and per power L. And given a certain J, T mu W of J at state I, the ith component of T mu Wj, is obtained by forming a weighted sum of powers of T mu, of powers of T mu, weighted with this W weights, which add up to 1. Okay? Now the thing is that you can solve this or solve this, they're the same. They have the same fixed points. If you have a fixed point of this T mu, so certainly a fixed point of this T mu W, and if T mu is a contraction, and you have a C, then T mu W is also a contraction, and if you have a fixed point of T mu W, it's also a fixed point of T mu. So solving one or the other gives you the same solution. However, solving this weighted equation has some advantages when you go into the approximation context. And for example, TD lambda involves a weighted mapping T mu. So there are two differences between this equation and that equation. The first one is that this one involves multi-step mappings, and this is an old idea, it underlies TD lambda. The second idea is that we have state-dependent weights. The W depend on I, and this is a new idea. This is our idea. And we need this in order to make the solution of this type of weighted equations more flexible and to apply to aggregation in particular. Okay, so let me just review some special cases. In the classical TD lambda algorithm, we try to find a fixed point of this mapping piece of lambda, which is a weighted, a geometrically weighted sum of powers of t, and now I'm dropping the mu index, but it's always a single policy. So the weights here are not state dependent. Okay, they are the same for all states. A possible generalization, and there are other generalizations, is to introduce a different lambda for different states. And that has some advantages. Why would we want to do that? Well, for some states, we may want to look longer into the future. TL sub j is a multi-step mapping that corresponds to an L-step dynamic programming problem. For some states, it may be essential to reach forward a great deal in order to understand what's going on. In others, it's not so essential. So we may want to tailor the look ahead to the state if we have some prior knowledge about the problem. The second idea is that using state-dependent weights may facilitate the simulation process. If we want to find a fixed point of TW by simulation, using state-dependent weights may give us flexibility that can be exploited to design new algorithms. And this is true in the case of aggregation. Okay, a third direction of research. We've talked about Seminorm projections, generalized Bellman equations. The third direction of research has to do with how you solve by simulation the weighted Bellman equation. We draw motivation for this from the classical TD lambda, TD sampling. In TD lambda, the weighted Bellman mapping is given by this formula here. And the way we find a fixed point by simulation is to simulate a single infinitely long trajectory. So we start at some state and we generate an infinite trajectory. We assume that the Markov chains are ergodic, so the initial state doesn't matter. We take this long trajectory and then we move the start point forward and we create many infinitely long trajectories with different start points. Then we average them in certain formulas and out comes a simulation version of the Bellman equation, which we can solve by methods called LSTD, LSPE, various methods, and we can base our solution on a single infinitely long trajectory. However, this does not work well in the aggregation context. In the aggregation context, we have regular states and aggregate states, and I'll give you a figure to explain this shortly. It just doesn't work because TD sampling matches well with the regular transitions, but not with the aggregate state transitions. So in place of TD sampling, we introduce a free-form sampling. Like the name suggests, it's anything you want it to be. You generate many trajectories, many short or long trajectories. One-step trajectories, five-step trajectories, 1 million step trajectories, and you may even segment them to form shorter trajectories. So the idea is that a trajectory of length L corresponds to a cost sample corresponding to an L-step dynamic programming problem. We want to form a simulation-based approximation of a weighted sum of these powers. So what we do is we generate a lot of samples corresponding to these powers and then combine them. And depending on how many samples we have of each length, we get these different state-dependent weights. Now, these are short trajectories, so the starting point of the trajectory does matter. And once you finish a short trajectory, then you go back to the beginning, select another initial state, another trajectory, and you can use an arbitrary restart distribution. And what this restart distribution will do will control the state-dependent weights and also the coefficients of the associated Seminorm. So all of this connects well with state-dependent weights, and that's what it is. Okay, so this finishes my overview. Let me give you some references. The idea of simulation with short trajectories and restart as a means was introduced as a means to control exploration in this paper here. Jenny and I wrote a long paper 2 years ago on these weighted Bellman equations and Seminorm projections. And I have a book from 2012 which has all of these ideas but with limited analysis. The book was published simultaneously as this work was being done, and was also, these ideas were thrown in as an afterthought, and hopefully they will be written up in a more extensive way. Okay, so now I'd like to say a few things about aggregation and how Seminorm projections come in. Okay, so suppose you have a subspace of basis functions spanned by basis functions, vectors phi r, where r is an s-dimensional vector of weights. Now, a Seminorm projection is a projection with respect to a norm where the weights of the different components of J may be zero. In other words, a weighted Euclidean norm has exactly this form, but all the sides have to be positive. A seminorm is one where some states do not receive any weight. Psi is zero. Now, of course, that means that when you project with such a seminorm, you neglect some states. However, you may you may not neglect neighboring states, and the cost of these neighboring states may keep the cost of the states that you neglect within reasonable bounds of approximation. So this is an ideal generalization. You select a few select states and you get good approximation for those, but then for the other ones you can get also good approximation because they are similar in neighborhood. So that's what we mean by a seminorm. And the idea of a weighted Bellman equation is to control the variance of simulation. If you look at TD lambda and the basic idea associated with that, and you consider this lambda mapping with lambda between 0 and 1, if you find the solution of this projected equation, it does depend on lambda. For lambda equal to 1, close to 1, the solution of this equation is the direct projection onto the subspace. As lambda changes from 1 towards 0, the solution traces an arc on the subspace, the approximation subspace, and the difference between the closest approximation, which is the direct projection, and the solution of the projected equation is called the bias. Okay? So for lambda equals 0 or lambda close to 0, you can have very substantial bias. And there are some devastating examples that show that the solution between lambda, for lambda equals 0, lambda is 1 can be vastly different. For lambda equals 0, you can get pretty nonsensical solutions. So the bias is an important issue here. You don't want to have large bias. At the same time, as you try to solve this equation by simulation, there's simulation noise. And the simulation noise is large when lambda is large. Because for lambda large, you look far into the future and the noise accumulates over time. So this is a well-known trade-off between bias and variance. You would like to have large lambda for good approximation, but small lambda for small bias. That's the motivation for having multi-step mappings. And that similar motivation carries through to the case of seminorm. There's nothing, as you pass from norm to seminorm, this picture stays the same. Okay, now let's get into aggregation and see how all this takes shape within the context of aggregation. Like I said, aggregation is an old idea whereby you have a certain system that has many, many states, from I to J, with transition probabilities corresponding given here, and you introduce aggregate states, which are much fewer, and you introduce a disaggregation mechanism for going from the aggregate states to the original states and back. From J to an aggregate state Y, you go back by interpolation, essentially, and there are these probabilities, phi J, Y, which form the matrix phi of basis functions. The disaggregation probabilities are the matrix T, and they give you sort of a degree of membership of original states into aggregate states. Now, what you choose as aggregate states is entirely up to you. There's no restriction. You introduce those aggregate states, aggregation probabilities, disaggregation probabilities, which are entirely arbitrary, except for the fact that they must be probability distributions. And you form this composite system with both regular states and aggregate states. And the way the system goes, you start at an aggregate state, you move according to these disaggregation probabilities to a regular state, then move according to the original system probabilities, transition probabilities, and back to an aggregate state. So if you want to simulate an infinitely long trajectory, you start here, you go down here, then you go back again, and so on. So an infinitely long trajectory must pass every third transition through this aggregate state. It's not like the same as an infinitely long trajectory of the original system. Moreover, in this aggregate problem, we have two Bellman equations, one corresponding to the vector of costs for the aggregate states, which we call R, and satisfies this equation here, with T being the mapping corresponding to the original system. And there is also another Bellman equation that corresponds to the original states, which is this one here. This is a long equation, right? This one is short. This one is very long. And it has this form, this projected form. So R is the cost vector of the aggregate states, phi R is the cost vector of the regular states, and there are also natural multi-step versions that you may be interested in because you would like to have a bias variance trade-off, whereby you introduce either a lambda parameter in the case of TD, or a more general W parameter for this equation here. So in the context of aggregation, that's what the Bellman equations are in their generalized versions. Let me give you some examples of aggregation, just to provide some context. The most common type of aggregation is called hard aggregation, whereby the aggregate states are just disjoint subsets of original system states which form a partition. In hard aggregation, you have a big state space, and you partition it into groups, into aggregate groups. And so, for example, in this picture, you have 9 original system states, and you group them into 4 groups. And this is one aggregate state, another aggregate state, 4 aggregate states. Now, in hard aggregation, when you are at a particular state, original system state, you go with certainty to the aggregate state that you belong to. In other words, the phi matrix has this form of zeros and ones, corresponding to membership or non-membership of an original system state to the aggregate state. The D matrix is conformal with that, and so from an aggregate state, you randomize and you go to the regular system states within the corresponding set, but the probabilities of randomization are arbitrary. So this is hard aggregation, a classical form of aggregation that goes way back. There's another method for aggregation which goes even further back, and that has to do with discretization. You have a state space, and you take a few points in there, and that's a discretization, a coarse grid, so to speak. And the elements of the coarse grid are the aggregate states. So this is called discretization, aggregation with representative states. Out of the entire original space, you pick some representative states. These are the big black dots here. And when you are at an aggregate state, you make a transition, you go to the corresponding state of the original system, you make a transition to some state J, and then you interpolate to go back to the points of the grid. So this corresponds to a different kind of phi probabilities and D probabilities that are equal to 1 for the representative states. Okay, so these two extreme cases correspond to different phi and D probabilities, and there's an intermediate case which I think is very interesting, which is, I call aggregation with representative features. Here you have a state space, and the aggregate states are disjoint subsets of similar states. You group together states that are sort of similar in the sense that they have similar features, similar character. However, these groups do not form a partition of the entire space, and also they may involve more than one state. And this is, hard aggregation is a special case where you have this big dark circles form a partition, and aggregation with the representative states is a special case where each one of these corresponds to a single state. think about the states of a cube and think of an aggregate state corresponding to the cube being almost empty. Another aggregate state, the cube being almost full. You know, some states are in these two, and maybe a middle state where the cube is halfway full or something like that. That would be a characteristic example of this aggregation representative features. And now here's how we connect this to Seminorm projection. Let's consider the aggregation equations, which remember are two. There's one for the low-dimensional aggregate system and one for the high-dimensional system, and compare them with the projected equation. If this phi d is a projection, then the two are connected. And the result is that if the approximation is piecewise constant with interpolation, in the sense that we make a constant approximation within the aggregate states, and we interpolate for the other states, in other words, the phi and d probabilities satisfy this condition here, which basically says mathematically what this says here, then phi d is a seminorm projection, and the size of the seminorm are given by this formula. They are connected to the d probabilities, and S is the number of states to make them for normalization purposes. And all of the preceding aggregation schemes satisfy this condition. So for all of these schemes, the Bellman equations are projected equations as long as we are willing to accept a seminorm. Moreover, these equations have a contraction property if T has a contraction property. That's another nice thing about aggregation that's not fully appreciated. The contraction property is lost very often in the projected equation context, in the TD context, but in aggregation, the contraction property is maintained. This is very important algorithm. Okay. So remember, we're trying to get Seminorm projections to bring up some unification, and we're done with that. Now let's go into the simulation-based solution of these weighted Bellman equations. Okay, remember I talked earlier about TD sampling, meaning that that we generate an infinitely long trajectory of the system. Now in the aggregation context, you have both aggregate and regular states. So an infinitely long trajectory goes up and down from aggregate states to regular states, and every third transition is to an aggregate state. As a result, you cannot get this multi-step character that the projected Bellman equation demands. And if you try to use the TD approach with a constant aggregation, it just doesn't work. The formulas don't come out. For example, we don't have multiple transitions between regular states. So we introduced a different form of sampling. It's a special case of this free-form sampling. Remember that multi-step mappings involving powers of t correspond to costs of Bellman equations that are multi-step. So t to the k is associated with a k-step trajectory of original system states. So our simulation has to follow this pattern, whereby we start on an aggregate state, then we go for many steps forward, and then go down. And we get a k-step trajectory, which perhaps we could segment into smaller trajectories. But we would not be able to do that if we had an infinitely long trajectory. So, that's the way we do it, generally speaking. Generate trajectories like that of different length, and we can control the starting state here, which gives us a form of exploration. It introduces an extra control mechanism for controlling exploration, making sure that we visit to an appropriate extent all the aggregate states. Instead of, those of you who are familiar with off-policy methods, for example, this is an alternative to off-policy, generating simulation samples that are representative over a large subset of states. Now let me give you a couple of examples of how you would use free-form sampling to solve this generalized projected generalized Bellman equation with a general matrix W here. One basic method for solving this equation is by value iteration or projected value iteration involving an intermediate projection here. Here we're operating within the approximation subspace, starting from a vector field of Rk, and then applying PW to it, projecting down, and getting another vector in the approximation subspace. So this is an iteration between the coefficients of the vectors in the approximation subspace, an iteration in Rk. And it is a fixed point iteration for this mapping here. Now, of course, for this iteration to work right, I have to have contraction properties, which are automatically satisfied in the aggregation case, by the way. Coming back to this algorithm, okay, projection, TW is a linear map. Projection involves least squares, right? And if you write the least squares problem corresponding to this iteration, this is what you have. Rk plus 1 solves this weighted least square problem, whereby you try to match the right-hand side, the TW phi R, to this, and try to find the solution of minimum squared error weighted by the psi i's. Now the psi i's can correspond to a seminorm. Some of these psi's may be 0, actually. As long as this problem has a unique solution, there's no problem. There's no difficulty. Here, phi I prime is the ith row of phi, and notice that here this involves low-dimensional calculations, or at least, okay, we'll make it to low-dimensional calculations. Okay, this iteration here, to implement it by simulation, you have to view it as an expected value, with psi's being probabilities, and the simulation probabilities in particular, which are obtained implicitly by forming trajectories of corresponding Markov chain. Psi I will be the frequency of I as a starting state, and WIL will be the frequency of a trajectory of length L when I is the start state. And the mechanism is the following. Remember, we're dealing with a Markov chain. We choose a start state, IT. This is for the trajectory T. Then we generate LT transitions. This is the length of the trajectory, and we end up at state JT. Then we form the cost associated with this short trajectory, involving the transition cost from here to here, plus a terminal cost that corresponds to the terminal state. Now this is a sample, a statistical sample of the LT step cost of the system. Okay, so we generate many of those for t equal 1 to m, where m can be very, very large. We could generate some of those and then chop them up into pieces to form more pieces for efficiencies purposes, as long as there's some, this is done in a reasonable way. Okay. Now, the frequency of the start state is going to correspond to psi I, the coefficient of the seminorm, and the frequency of our start state length I and L will correspond to the W. W is going to be obtained from psi by dividing this with that. If you form now a least squares problem where you match empirical costs with the estimated costs and solve this problem, you get an optimality condition which converges to the optimality condition of the optimization problem in the previous slide. In other words, this is the problem we want to solve, and to solve it by simulation, we form this kind of simulation mechanism. We solve this problem here, and the solution in the limit converges to the solution of the problem in the previous slide. So that's how you implement LSTD. That's how you implement projected value iteration by simulation. And there's a similar way to implement LSTD. In LSTD, you solve a different kind of problem involving, okay, it's still a least squares problem, but it's different than the one before. And again, you form short trajectories, consider cost samples associated with those, form a least squares problem, which is a linear least squares problem, and in the limit, as m goes to infinity, you get the LSTD solution. So these are two examples, and there are other examples, other methods corresponding to optimistic policy iteration, other methods, free-form sampling methods corresponding to aggregation, and so on. So I think I'm going to conclude now. Okay, three main ideas here, but they all connect in unifying this area of approximate dynamic programming with cost function approximation. Seminorm projections, generalized weighted Bellman equations, and free-form simulation to match these. Both multi-step projected equations and aggregation, as well as other methods, fit this framework. And some of the highlights that I have presented are the connection between projected equations and aggregation equations. You can make this connection through seminorms. There are multi-step aggregation methods to the TD lambda type. I don't think that this has been previously known. People thought of aggregation as a TD0 type of method. A variety of sampling methods can be used. Free-form is free-form. It's free for all. Anything that you want, subject to minimal mathematical constraints, can be used. There's a more flexible treatment of the variance trade-off, and also a more flexible treatment of the exploration problem of having representative enough simulation samples to represent a broad variety of states. Finally, all of this is generalizable to a very broad field, which is the field of solution of general linear equations. You can't think of a broader field than this. You can use simulation-based solution of linear equations through this Galerkin idea in exactly the same way. Nothing changes except for formalism and contraction issues here and there. So there's I think this is true also of the existing methodology of approximate dynamic programming, like there's a TD lambda method for general linear equations, not just for Bellman's equation. All of this, I think, may become significant in the future. So that's where I'll stop. Thank you very much.
So before moving to the questions, and we will have questions, I would like to reiterate my thanks as well as the thanks of the general organizers of SSCI, and this time supported by the material thing, which is this appreciation and recognition plaque that was presented by Ivo, and I will present it now to the president. Thank you again for being here. So we are a bit late because of the run of the being late with the original plenary session, but we should still take questions. So, yes?
It's a general question. So by chopping the trajectory into pieces, do you get more statistics information? So does it enable more accurate solution? Just generally.
Well, I think you are exploiting to the fullest the information that you collect. You don't throw away information. You don't generate new information. I would put it that way.
I have a very particular question regarding your last remarks. So there are many engineering problems where it's very important to provide approximate solutions of linear equations very, very quickly. So moving from 20 milliseconds to 5 milliseconds. And my question is whether what you indicated, of course, for sparse matrices, like power grids. And my question is, what do you think about your last remarks? Is it the direction was to investigate or
I think it's an important direction. I always view it as an important direction. It hasn't been recognized as such by the community at large. But I look at the numerical analysis community that has been solving partial differential equations for decades, many decades, since the early 50s. And they are using the Galerkin method very widely. It's one of the principal methods. However, they cannot solve problems that are more than a few thousand of dimensions large. Here we're talking about dimensions of millions and billions and trillions, gigantic dimensions. And I think that if you want to go to dimensions like that, you cannot solve the Galerkin system exactly. And simulation is the right way to go about it. And by the way, simulations-based solution of linear equations is not a new idea. It was proposed by von Neumann back in the 40s, 50s perhaps. So it is the only way to go if you want to solve truly very, very large systems.
I am very interested from your topic, and I want to know if your method can be used to design for the control law for nonlinear system, a practical nonlinear system, how to design control law to use your Seminorm project.
It's not very clear. And I've thought about that. I think there's some distance between the control literature, what people call adaptive dynamic programming, and reinforcement learning. One is focused on continuous space systems, governed by differential equations or maybe difference equations, but still continuous space. Whereas the reinforcement learning, dynamic programming, Markov decision process community focuses more on finite state systems. So there's some gap to be bridged there between the two communities. And for the moment, the methodology is quite different from what I'm able to understand, although both of them involve forms of policy iteration, and policy iteration involves computation or approximate computation of the cost vectors of policies. So if you have some form of good discretization, then it may be possible to connect the two, but I don't think that has been done yet, and I certainly don't have the answer to your question.
And on that note, sorry, I think it's good to close now because we have only a couple of minutes left to get some coffee and then be back at 10:20 for the session. So thank you again. If there are more questions, you can just take them offline in the break.